All right, we are on part two of our directed graphs, and this lecture should give you everything you need for homework 7, although it's going to be a little compressed. But like for homework 6, we're giving you all of the code and just expecting you to, through our discussion today and practice problems, study and learn how to apply that code to a different set of related problems. So we're moving into directed graphs. So we introduced that, and we're going to look at the bigger challenge with directed graphs, which is finding the equivalent of these islands, these what we'll now call strongly connected components. Previously, we called them connected components in our undirected graphs. So that's our big topic for today. Reminders about dates. So we'll have a lab. There was no 25, but we'll have a lab today, due for Friday. And last drop day is tomorrow as well. I don't think anybody's in that situation, but I'd like to put that out there in case you're worried about that. And then we have our, I did it again. Sorry, guys. After Thanksgiving, so many things I got to fix every year. Tuesday after Thanksgiving, greater than Thanksgiving. So we'll have our homework 7 and our quiz coming up. Okay. And then lecture 27 is the one that we're going to miss on the 28th. It's so hard to remember. Or is it the 27th? Anyway, we'll drop a lecture, and I'm cleaning up the content on that, so we should have that shaken out here pretty quickly. Quick reviews. These are the classes we have explored so far. Homework 7, we're going to have another modified version of this. We'll modify the graph class today. And just like homework 6, you'll get the reference code for that in Canvas. So don't forget to go look at Canvas for your code when you're ready to dive into homework 7. We're going to replace this connected component in homework 7 with a strongly connected component class. We're going to study that today. And probably you're going to be interested in the depth first order. We're going to use that today. And probably for some of you, cycle finder as well. Okay, so these are, directed cycles. So these are the lectures L25 and L23 and L21. If you need to go back and kind of review what we're doing there. But all of that code will be in a linked place for you in your Canvas for homework 7. Okay. So this is what we're going to do today. Study depth first order, which we introduced last time, and then build on top of that. Okay. And once again, we're going to continue to use depth first search like we did in connected components, but we're going to modify it ever so slightly again for today's strongly connected components. So it's the backbone of so many things that we can do with just little changes here and there. And you'll notice it just keeps popping up all over the place. So recursion is just really, really crucial for understanding how to solve these kinds of problems. Okay. So we said last time all we did was did a minor change to our graph. We added this little Boolean thing that said is directed, yes or no. And only if it's not directed do we add the extra adjacency, okay? So if it's not directed, we need an adjacency in both directions. Otherwise, we just go from VA to VB. That's sort of our directed edge in that case, okay? So that was our change last time. And we said with that, we could just do path searching with our good old friend, the path class, because we're just still using the adjacencies to find that. So shortest path, any path, we can do that the standard way using the path class that we already had. Now we said that last time we talked about topological searching, and we said that depth first search using left-right parent, otherwise known as post-order traversal, is critical to generating the right order of traversal. And we're going to use that topological ordering today. We looked at it last time just in terms of dependencies of DAGs, like, hey, what class do I take first, and then next, and next, and next. But we're going to use that order today to solve the strongly connected component problem. So we still need to kind of, have this in our heads. What does it mean to traverse a tree in LRP or post order. It's like, hey, post means parent last. So left, right, and then parent, right? And so that's how we got that funky order coming out of that. But it basically gives us the children before it gives us the parents. So that is kind of key to, gleaning the topological ordering out of any kind of a graph that we're gonna pursue. Now, the graphs that we're going to apply that to today will have cycles, but it's still going to be a useful algorithm for determining sort of faraway leaves relative to, near leaves. So we're going to use it in our strongly connected component search, even though some of the graphs we're going to apply it to will have cycles. And we'll show you that with some simple walkthroughs today. Okay. So normally, when we unwind from recursion, we said we would go from the bottom up, and that's how we get our topological ordering, okay? So we tend to use a stack just to build that reverse ordering, but you can do that with a couple other things. So I won't take you through all the steps of this, but the idea was perform a depth first search, right? And no cycles if it's supposed to have no cycles, but we'll allow cycles today. And we return the visited vertices in reverse post order. In other words, we reverse the post order traversal, and that's going to give us the topological ordering. Okay. So that's kind of I won't take you through the entire walkthrough on this. This is our slide from the last. But when we say post order, we get this. And when we reverse that, of course, that's going to be the topological ordering. Okay. So post order and reverse post order. I find it very confusing, which is why I try to highlight the difference between those two terms. Okay. Let us take a look at, and we found cycles. We said we did a little other trick, which was we kept an additional piece of information in an array to basically determine which nodes we visited on our downward journey through recursion. And if during that downward journey of recursion, we wrapped around, right, and visited something we already visited on the way down, then we know that's our cycle, okay? So we just had to keep a little extra information in the directed cycle class in order to find out if there was a cycle or not, okay? This will be important for one of the parts of homework 7. So when you're looking for an Eulerian cycle, this is that proverbial street cleaner that wants to go through and clean all the streets without ever repeating any edge, right? First, you need to find out if it's a cycle. Then you need to find out if it visits all of the edges in a particular strongly connected component. So you will need this class to solve that last part of your homework 7 problem, okay? So keep that in mind for reference. Again, we keep an on-stack array to help us do that process. I won't take you through it all again, but you can kind of go back to our previous class to kind of go through that in more slow fashion. But that's the class we need in order to find a cycle, okay? So just kind of speed through that a little bit. So today, we're going to talk about strongly connected components, often abbreviated SCC. So one of the things we need to be able to do to apply the algorithm we're going to look at today is reverse a graph. So we talked about this a little bit. Now we're going to implement it in our graph class. So it's going to be just another method inside of our graph class. And in C++ at least, very often we use the double colon as a way of saying this is the class that owns this method. So it's just shorthand for saying, yeah, this is a method we're going to put in that particular class. Okay? So we're going to call that strongly connected component. Okay, so it is specifically meant for directed graphs. So that's why we're going to apply it. We'll talk about why we need that. And it will be what you need along with all those other classes we just reviewed for your homework 7. Okay. So trying to put it in context, a strongly connected graph is any one where any two vertices on the graph can visit each other and get back home again. So if we look at the Bay Area and we consider the bridges, right? So the different regions are the vertices and the bridges would be our edges. And if we think about this, in the no toll direction where we don't have to pay tolls in the Bay Area, that is a strongly connected graph. And the reason is because anybody can visit anybody else and still get back home again along those directed edges. So in other words, without paying a toll. This is one of my favorite things to do in the Bay Area is go driving around and never pay any tolls. So we can do that. It's really great. So that is a strongly connected component because everybody can visit everybody else and get back home. Okay. So whenever we evaluate that property of a graph, one way to think about it is just pick any two pair, right? And then find a path between them and then find a path back. So the path back may not be the path that took you there, but at least it gets you back home again. Okay, that is the definition of a strongly connected graph where it's the maximal set of vertices that all essentially are connected in that way. So in other words, if these two are connected in that way and these two are connected in that way, then that implies that all three of these are effectively connected in that way. Okay, and so that if we can find that number of vertices in any graph, then we now know, hey, this is a part of that graph that, there's a lot of connectivity in that area. Okay, so that's the idea of a strongly connected component. And there might be one-way, bridges that you cross over, you can never get back again. And we kind of talked about that in our homework 7. So graphs do have that. And, you might get over here and here's another strongly connected area. And it's all part of the same graph. It's just we have this weak link between these two islands, as it were. Okay. So that's the idea that we're pursuing in these directed graphs. And if I reverse the graph, right? So this would be our paying toll direction, not my favorite direction to go, but that's still a strongly connected component. So this is an important property actually that we'll see in this algorithm we're going to look at is if you have a strongly connected component and you reverse that graph, it is still a strongly connected component. Okay. And I believe there are some proofs to that effect, but we're going to kind of lean heavily on that in this algorithm that we're going to look at today. Okay. So they are both going to be strongly connected. If one is, then they both are. Okay, so let's take a look at a couple small graphs. So, and you're going to be presented with these in your quiz. They're all relatively small, but it's like, hey, what are the strongly connected components in this graph? Okay, so A and B can reach each other. B and C can reach each other. So therefore, A and C can reach each other, right? So can D and B reach each other? Yes, that works, right? So if we were to do that sort of n squared pairing, right? I got 4 vertices and I'm going to sort of check all of them against each other. Then we'd know, yeah, okay, these things are strongly connected, okay? It does not require that, it be the same path to go back again, okay? So that whole thing would essentially be considered a strongly connected component, okay? So there are some good examples of this in your Quizlet sets, and all of these or many of them are taken right into the quiz. So it's just a matter of seeing the pattern, which you'll see after a while. So feel free to click into those and take a look, or just use all your quiz turns, and I think you'll end up getting the sense of that pretty quickly. Okay. Now, the tricky one that often trips people up, including me, when I'm jumping in after a while, is if you have vertices that are not connected to anything, then those vertices individually form their own strongly connected component. Okay? And that is really like we saw with homework 6. If you've got these islands out there with just one vertex in it, that's a component. Okay, so strongly connected components are the same way. If there's just one vertex, that one vertex is a strongly connected component. Okay, so remember that when you're thinking about your homework 7. Okay, but let's do the groundwork for reversing a graph because we're going to need that. And it's just, a little bit of code, but notionally, the idea is simple, right? Take every edge and reverse it. Okay, and probably we're going to make a copy of that graph. So we want to say, make a new one and reverse it because we're not trying to go backwards to an undirected graph. We want to have a duplicate graph that represents the reverse. So how are we going to do that? we're really just going to go through, and for every adjacency, we're going to create the opposite adjacency in a new graph, okay? So here is our existing original graph, right? So there's our adjacencies. So 0 points to 1 and 0 points to 3, right? So here's the 1 and the 3. So if I want to build the opposite graph, the first thing I got to do is create the adjacency array, okay? And then fill it in. I got to walk through this 0, 1, 2, 3. And for each adjacency, I have to go to this vertex and add a adjacency to the 0, for example, right? So if we're doing this edge here, it's going to end up over here, okay? So like so, right? So it's just a loop, right? But we got to kind of build that into our graph structure so any graph can essentially create a duplicate version of itself and go, here's a copy, right? Here's a copy that you can use. That's the reverse, okay? So a little bit of looping to actually do that. And there's our reverse graph, okay? So let's take a look at the code for that. It's pretty quick to do. And it's going to be, we're going to do a little bit of pointer magic again. So we're going to say new graph to create our entire graph structure on the heap. New always gives us a pointer. So that means that this is a pointer to this graph structure floating somewhere on the heap in C++. So graph star, not graph, because new always gives us a pointer to whatever that little blob is. So imagine it's like I created a blob that represents a graph, and now I have the pointer, and I'm going to store it over here in this variable called grev, okay? So we say grev points to that on the heap. Okay? So we'll look at that with a little more clarity in the code. That's different, of course, than doing this, graph space g. That's saying create an automatic variable that's going to go away after the end of the scope of this function or method or whatever, okay? So this one doesn't go away until we delete it. This one goes away at the end of a function or constructor or method, okay? So we want to do this one because we don't want this graph to just go poof. We want to hand it off and say, hey, here's your graph. You go deal with it, right? So whoever we give that pointer to, it's their responsibility in C++ anyway to eventually delete that graph, okay? I'm not going to try to delete that graph for them, okay? As opposed to here where it's just going to get cleaned up by C++. So we're going to do that, and we'll see that in code and inside of our method for our graph. And we'll just test to make sure that things get printed out. And think about, while we're doing this, think about the cost of doing this, right? So N, I probably should use a V. It's more typical to refer to the number of vertices as V and E. So what is the cost in terms of the total number of vertices in the graph plus the edges to reverse the graph, right? So let's take a look. Okay, spare our eyes here. And I think increasingly I'm realizing that if you want to use the canvas sort of iframe for our practice problems, you probably have less stuff going on around the outsides, but it's entirely up to you. So I'm just going to search for my to-dos, right, like usual. So inside of the graph class, we're adding a reverse method, okay? So here is our graph class with all of its glory. It's destructor. We won't describe these in too much detail. It's kind of more advanced, but this is preventing us from trying to make a copy automatically. If we don't take away these capabilities, C++ creates a shallow copy of our graph structure. So that's a very dangerous thing. So in C++ anyway, we often take away that capability. Okay. So if you're curious about that, ask me. I'll go into more detail. But here's our reverse graph. So I'm going to create a pointer to a graph structure. Let me make this a little bit bigger. So I'm going to create a pointer, call it grev. And I'm going to say grev equals a new graph, right? I'm going to say, here's how many vertices, and I'm directed, so you're going to be directed. So this is like saying this instance is directed. So I'm going to pass that into the new graphs constructor as well. Okay. Not hugely important, but just explaining what's going on there. And now we're going to go through the adjacencies for this graph, right? So I'm going to go from VA0 to P count. And then for each VA's adjacency list. So TV gets the adjacency list for VA. And I'm going to say, okay, my new graph arrow, because it's a pointer, add edge method. I'm going to go backwards. I'm going to go TV arrow ID to VA. So I'm adding that reverse adjacency to the GREV graph, okay, for every linked list inside of my normal graph, right? So I'm inside of my own normal graph, and someone's called up my reverse method, said, hey, give me a reverse of yourself. So that's what we're doing here, okay? So when we get down to the bottom, we of course want to return GREV, which is the pointer to this brand new graph on the heap, okay? So I'm handing it off and saying, there you go, have fun. There's your new reversed version of me, okay? So we'll come back to use that here in a little bit. So that's our method. Now down here in main, right, while we're doing our input loop, we're collecting edges, and we just want to create a reverse graph down here. So I'm going to say my reverse graph equals G dot reverse, okay? And it's just that easy. Now my rev is a pointer to a brand new graph. And so I can say my reverse graph arrow, because it's a pointer, print adjacencies. So these adjacencies should show up as the reverse of the adjacencies of our normal graph. Okay. Now, again, I don't want to turn everybody into a guru C++ developer, but you might be curious, why is this graph G dot print adjacency and this graph is G arrow print adjacency? Well, the reason is because G here, right or wrong, was created as not on the heap. There's no new there. There's no pointer. So G is an instance. Down here, GREV is a pointer to an instance. So in C++, when we have a pointer to an instance, we follow it with an arrow. And if we have a regular instance, G, we follow it with a dot, okay? So apologies for the remedial stuff on C++ there, but I realize it's kind of dense. So now we should be able to run this, unless I've goofed up. Okay, so I'm just going to copy paste in the whole graph. I could do it individually, type it in. I'm just going to paste, enter, and it's going to kind of build the graph one adjacency at a time. And so this is our normal graph, 0, 1, 1, 2, 2, 3, 3, 4. And if we have a 0, 1, that means we should have a 1, 0. If we have a 1, 2, that means we should have a 2, 1, etc. So we can kind of see we got effectively the reverse graph that we need. Okay? So no real rocket science there. We're just kind of doing the groundwork that allows us to do this algorithm that we're coming up on here shortly. Okay. So here's that, all laid out for you. Okay? And again, we're returning a pointer to a graph. GREV is a pointer to a graph. So all these apples and apples kind of line up. Okay. So that's creation of a reverse graph. Now we have this baked into our graph class, and we're going to use it for this algorithm that's coming up, okay? So we're going to, in the construction cost, if you think about it, we loop through the number of vertices, and for each vertex, we loop through the number of edges. So really, it's a V plus E worst case cost, okay? And it's really pretty tightly bound, right? So it's really, that's the cost of what we're going to have to do to build this graph, which is not terrible. We would call that linear, okay? So even though it's V plus E, it's still a linear time cost, okay? So if we have lots of edges, it's maybe a little more, a little bigger number, but it's still a linear cost as V and E grow. Okay? And then, so this was our kind of just primer on the arrow versus the dot thing. Okay. Okay, so let's go ahead and talk about the strongly connected component algorithm. So again, we have this idea of equivalence relations, and we could do an n-squared algorithm pretty easily. Okay, so here in this graph, we have, one giant strongly connected component. Okay, so but not all graphs, of course, are going to be that way. Okay, so we want to actually, determine what those strongly connected components are. And we're going to do it this way. So imagine that we just decided to test every pair against every other pair, roughly n squared. We'd say, is there a path from 0 to 5? So we could find a path from 0 to 5 or determine if they're connected. We've done that in the path class. And then we could flip that around on the reverse tree and do it that way, or not on the reverse tree, just the same tree, right? 0 to 2. So if we did all that, it would work. It would give us the answer, but that's kind of n squared in terms of the number of vertices that we have to check. But that would tell us whether or not that thing's a strongly connected component. Okay. So we could find out that information, in a relatively brute force way. But these would be what we call the SCCs. And the number is not really so important. It's just a unique identifier. And it tells us the order in which we discovered them, for example. But that order could change depending on the construction order. We'd still get the same strongly connected components. We would just, maybe see them numbered differently. So I could have 1,000,000 vertices here and still only have 4 strongly connected components. Okay. So in the crazy taxi homework, I think you got like 1,000 vertices. I think you're only going to really have like, I don't know. I'm trying to remember. There might be 100. I can't remember. I'll have to check, but it's not a huge number, right? It's really about the groupings or the islands. And these little bridges, think of these as sort of connection points between the islands, okay? So we start counting at 0 just because. And so the highest numbered strongly connected component is 1 less than the total number of strongly connected components, just like homework 6, okay? So that's kind of our basis. So here's another example. So if I were to sit down and just say, okay, trace this through with your fingers and try to figure out what are the strongly connected components here. Well, there are no cycles in this graph. So if there are no cycles, then there's no way for any vertex to get back to its starting point, which means that it doesn't mean there are no strongly connected components. It means there are many strongly connected components. There's actually 14 of them here because each individual vertex is an island. So there's no strong connections, but essentially that results in a whole bunch of strongly connected components, okay? This is just one thing that ends up getting forgotten a lot. So we got to watch out for that, okay? Here's another one. How many strong connected components here? 7, right? Because there's no cycles in there. So we can't kind of get back home again. So this is sort of a rarer example. Now, what's really cool, I was curious about this, and a math teacher, some of you know, I'm blanking, Professor Zafran, thank you, mentioned this in the hallway. Pure coincidence. They're looking at the data for the connectivity of the smallest worm whose brain or nervous system has been fully mapped. And it's a directed graph. And there's only about 150 vertices in this worm's nervous system. And they have mapped all of the connections, the synapse connections, okay? So that is called connectomics. It's like genomics, but using a directed graph from actual mapping of this creature's nervous system. But it turns out that, and that's called the Open Worm Project. If you're curious about it, it's kind of funny. But they are literally simulating the full living, thinking and operation of this worm because it's actually doable. But there has also been a fully mapped directed graph of a fruit fly's brain. Okay, now we're talking about 150,000 vertices, and I don't quite know how many synapse connections, but these are directed graphs. And so the fruit fly brain is pretty much a model for studying the human brain. And guess what? Strongly connected components are like connected nerve centers like cerebellum and hippocampus and things like that. So finding these regions, and there are other algorithms that are worth studying too, but finding these regions in these fully mapped brains is a pretty fascinating area of study. It's only about 15 years old. So they've only really recently been able to map this stuff. So these are some pretty interesting things. Of course, strongly connected components can be used for studying ecosystems, software modules, the analysis goes on and on. But this one's pretty young and it's pretty interesting because we really haven't had too much access to that kind of data. And the human brain mapping project is underway now too. It's going to take many years before we have the full map of the human brain or a human brain, but it's going to be a directed graph, which is pretty darn cool. So studying these graphs with some of these algorithms is still a relatively young field of science, which is pretty cool. So I think we've seen this before, but this is a Python module dependency graph, right? This is just showing you, yeah, software can be pretty complicated. So if you're interested in Python libraries or modules, there are some pretty complex dependencies there that can lead to some very challenging debugging projects, depending how big your project is. But these are all directed graphs as well. Okay, so let's just put the algorithms side by side. The connected component and the strongly connected component use the same data structures, was visited and component ID. So except here, we're counting strongly connected components, and over here, we're counting connected components. So we're going to follow the same strategy is go through the graph, and as we encounter vertices, tag them with a component ID, right? And at some point, we're going to increment the component ID to say, okay, we've found all the ones in component ID 0. Now we'll go on to component ID 1, component ID 2. So the ID number is not as important. It's just a counting process we're going to use to tag these things, okay? So the question is, how do we do that? Like, how do we decide when it's time, and how do we traverse this graph so that we get the components in this way? And so the battle has always been to do this in linear time rather than quadratic time. So n times n pairings would be quadratic time. And it was like that for quite a while, up until about the 70s. And that's when people started coming up with interesting ways to do this in linear time, which is significant, right? If you think about it, going from quadratic time to linear time. So Kosaraju-Sharir is the one we're going to look at. It's a two-pass algorithm developed in the 80s, and it uses topological sorting of our directed graph as a foundation for solving this particular problem, okay? So let's take a look at our original graph and kind of introduce the steps. So the main ideas are, if we reverse the graph, we know that it's going to have the same strongly connected components. So we're not breaking the islands apart in any way just by reversing the graph. So that's a crucial thing, okay? So what we want to be able to do is essentially build what we call a condensed graph. So these are just a different way of looking at these islands, but think of it as almost like a topological sorting using some other traversal strategy other than just 0, 1, 2, 3, 4, 5, 6. So we're going to use depth first search. We're not going to just start with vertex 0 and then go to 1 and go to 2. We're going to do something a little different. We're going to do a topological sort and use that topological sort to guide our depth first search algorithm, okay? So that's the Kosaraju algorithm, is we reverse the graph, perform a topological sort on the reverse graph, and build a stack, that stack that tells us what order we want to take our classes in. And that's the order we will use then to run a second depth first search on the normal graph. So we'll use the stack ordering from step 2 will guide the order in which we do this depth first search on the normal graph. So to get that order, we got to use the reverse graph, and then we come back and apply that second one, okay? So let's just work through some really simple examples before we go to the code. So here's a pretty easy graph. This graph has 1, 2, 3, 4 strongly connected components because nobody can really visit anybody and get back home again, okay? So it's kind of a one-way path from island to island to island. So let's apply our algorithm to that. We reverse the graph, okay? We do a topological sort. So let's remember what that is. We just pick a place and we recurse as far as we can go. And then on the unwinding, we write down where we came from. So 3, then 2, then 1, then 0, okay? So that is our top-down reverse post order is 0, 1, 2, 3. So what we're going to do now is use that. Now, coincidentally, that's in sequential order, but that's just coincidental. We're going to use that topological order to run our final depth first search on the normal graph. So over here, we start with 0, and we try to do a depth first search, but we don't go anywhere, right? Because we can't go backwards on that edge. So that's SCC 0. That one's done. Now we'll just click forward and go to the next vertex that's unvisited, which is 1. We also try to go in a depth first search on that, but we can go nowhere. We can't go back because this has been visited, and we can't go that way because that's in reverse order, right? So we're done there. That's another island, okay? And you can kind of see the pattern, right? We are blocked off by the already visited, and we're blocked off by not being able to go backwards along that directed edge. So we end up with 4 tagged vertices that fall into their own islands, okay? It's kind of a trivial case, but it shows that the algorithm isn't broken for that trivial case, okay? So let's look at 2 more examples. So we have 4 total components tagged from 0 through 3. Okay, this is in 0, this is in 1, this is in 2. Just coincidentally, it's the sequential order we have on the screen. But let's flip it around, okay? So there's the reverse graph. Notice the arrows are pointing down this time. It's a little trickier. So we do the topo sort. So go as far as you can and then unwind. Well, that's pretty trivial. Go as far as you can and unwind. Well, we can't go to 0 because it's been visited. So our topo order is going to basically be 3, 2, 1, 0. So now we'll use that order for our final depth first search on the regular graph. So we'll start at 3. How far can we go? Nowhere, right? We can't go backwards on that edge, okay? Then we go to 2 because we're processing in topo order. Can't go, that's been visited, can't go backwards. So once again, we end up with the right answer. These are 4 individual strongly connected components, each tagged individually, okay? Seems pretty simplistic, I know, but just getting ourselves warmed up. So let's look at our third example. So now we've got kind of 2 islands, right? Strongly connected, strongly connected. So if we run our algorithm, we should sort of get a 0 and a 1, or a 0 and a 1, right? But there should only be 2 strongly connected components here. So here's the reverse graph. We run a depth first search down to 1 and unwind. That's a 1 and a 0. Now we try to check 1, but 1 is busy, so we go visited, so we go to 2, traverse, unwind, 3, and 2. Now we have our topological order, okay? So let's do our final DFS using this order. So 2, where can we go with the 2? Oh, we can go to the 3. Now they're both visited, so they're both in component 0. But we can't go any further than that. And if we try to go to 3, it's already been visited, so we'll skip it. Then we go to 0, right? So we check this, we check this, we check this. And now we can travel down, mark both of those as component 1, and we're pretty much done at that point. So we have total of 2 islands strongly connected. Okay. One more. Okay, this one, actually 2 more. So what did I do differently here? I know these are a little bit dry, so hang in there. 0 and 1 are connected, 2 and 3. So I'm just gonna go fast forward through this. 0 and 3 should be in an island, and 1 and 2, right? So reverse graph, create our topological order here, like that. Use that order for our DFS. And as long as it's not visited, right? But 2 is now visited. We already visited it by virtue of the first depth first search. So skip it, do the 0, right? And once again, we get a correct answer. One more example. This was the one with the cycle. So promise we won't go beyond this at this level of detail. But let's just try this one. Reverse graph, okay? Let's do our topo sort. So I start at 0, go as far as I can go. Let's say I go to the 2, then to the 1, and now I unwind, right? So I'm going to unwind from here. So that's the 1, then the 2, back to the 0, okay. And I can't visit the 1 or 2 again, so I end up at the 3, and that's as far as I can go too. So that's my order. So we're going to go. So if these were classes, even though we have a cycle, the class you got to take before every other class here is the 3. That's why it's on top of our topo sort there, okay? And then finally, we use that to do our depth first search on the regular graph. And that's going to give us our components, right? Like so. So we end up with 2 components. Okay. So nobody expects you to kind of, go, aha, I get it, and that's pretty complicated stuff. And, no one knew that for a while until somebody came up with this idea of doing the topological sort. But, it made things possible in linear time, which was a pretty significant thing. So let's take a look at our new strongly connected component class. We're going to combine essentially the topo sort inside of this thing, okay? We're going to have a topo stack anyway. We're going to get our reverse graph inside of our constructor. So here's our strongly connected component constructor. We lay out our, component ID and was visited. We get a reverse graph, okay? And then we're going to go through and in step 2, we're going to build the topological sort. And then we're going to do our DFS based on the stack, okay? So this is going to build the stack, and this is going to use the stack. So those are our 2 key phases, okay? So this part of our code is going to fill up this topo stack, and this part of the code is going to pop it out, okay? Pulling that stuff out. So let's see if we can do this. This is our last practice problem for the day. It's kind of a gnarly one. So let me see if I can do it. There's a number of pieces of code I need to do. But if we want to test this graph, which should be strongly connected, you can just use those numbers there. So let me see if I can kind of fill in the missing pieces here, okay? And I do indeed hope I got that. Okay, so let me see if I can make it just a tad bigger. Again, this is the Kosaraju. This is a famous little graph called TinyDG. So it's part of the Princeton course, and there are a number of pretty famous data text files. So tinydg.txt is a small directed graph. We'll also see some other ones that are a good deal bigger, but it's sort of the data you see here. So let me look for my kind of to-do. So I'll search for TODO like usual. Okay. So we're going to create our stack. Okay. So this is our stack, and it's inside of our new connected component class. Okay. So we're going to create a stack. It's a data member. Okay. We're going to do our reverse from our regular graph, right? Somebody gave us a regular graph. We're going to reverse it, store a pointer to a copy of it, right? Because we did that earlier. Okay. And then we're going to go down here, allocate our vertex arrays, initialize them. And we're going to say true. Yes, I want to use or generate the stack using our depth first search function call down here. So DFSCC is going to get called twice. First, it's going to get called on the GRev. And yes, or true, you could just say true there if you like. We're going to call and build the stack. So that's a little flag that tells this routine, this time I want you to fill up this stack up here, okay? This stack that we allocated, sorry, all the way, where'd it go? Where'd it go? Here, right? So we're filling up that stack, okay? Now, once we're done with that first pass through with the reverse graph, we're going to say don't fill up the stack, just unfill the stack. So we're going to say false, right? And we're going to say while the stack is not empty, grab what's on the top of the stack. That's us peeking at the stack, and then pop it off, okay? So we're just going to peek and then pop, right? Or peek, print, and pop, okay? And then we're going to say if this thing was not initialized, or not visited rather, then let's follow the regular graph, right? And start with next topo vid, okay? So this is what we were doing kind of in that, from that topo sort list that we had on the previous page. So visit everything you possibly can until you get stuck, tagging it with the current component ID as you go. And when you come back from that, increment the component count so we can go around and do it again, okay? So we'll just keep going until we process the entire topo stack there, okay? And when we are done, right, we've got our component IDs just like we did for homework 6, okay? And eventually when someone deletes our component, then we'll get rid of that stuff, but we're going to let it hang around for a little while. So let's take a look at the depth first search SCC. It's pretty straightforward. It's what we've done all along. We're just going to mark something as visited, tag it with the current component, get its adjacency list, and then for each vertex in it, we're going to try to recursively call and just keep repeating over and over again, okay? And we're passing down the same do stack true or false that somebody gave us up here, okay? So that's it for our DFSCC, and I feel like there's more stuff down here, but let's see, maybe down in main, just one or two things. So here we are, we're building our graph, okay? It's a regular interactive input to build the graph. And when we're done building the graph, we'll perform our strongly connected component analysis. So strong component. Is that what I called that class? Sorry, you'd think I would know by now. Sorry to make you jump around. Strongly connected component. Okay. So let's create our strongly connected component here. Okay. So SCC passing in an address of my graph structure and then printing out its components. So they all should be in the same component if I use this simple example here, right? Okay, that should all be in the same component. So let's run it. Yep. Boolean stack false. What did I do wrong? Note bool stack previously declared. Oh, think I redeclared something on 305. Sorry, I'm gonna get something wrong. 305. So this has already been declared, so I don't need to redeclare that again. Okay, there we go. All right, put in a graph, let it run. It's going to build up the graph. And, uh-oh, let's try that again. How many nodes do you want in your graph? Oh, I missed the 10. Okay, let's try that again. Um, I'll say 10. Actually, is it 10? Sorry, guys. Let me go check. It should have 4. So it should be a 4. And then we can paste that in. Oh, yeah. Paste that in. That should be our full graph. Okay. Now we're building our regular graph. And we're running our SCC constructor. Okay. And the adjacency, the strongly connected components are all in component 0. So vertex 0 is in 0, 1 is in 0, etc. So simple graph, right? We could take the tiny DG with 13 and run that. I don't remember how many strongly connected components we get there, but we're going to take a look at here in a second. So I'll just let that crank through, jump to the bottom and see who's in what component ID at the very bottom there. Okay. So we've got 0 is in 1, 1 is in 0 all by itself. Got a bunch of others that are all in 1, right? So this should feel familiar. Some are in 3, some are in 4, some are in 2, okay? So hard to visualize what that graph looks like. We'll look at that on the screen here in just a second, but that's what the correct answer should be there, and I think we matched that okay. Okay. So I think I have that on a page coming up here, okay? But pretty complicated, but still just different tricks with the depth first search and storing data in clever ways. Okay. So step 1, step 2, step 3. Okay. And then some cleanup. Okay. Now, let's see. Oh yeah. And this was just our DFSCC in our constructor, okay, which we saw. We looked at that up close. And then here is our kind of second step there. Okay. Step 3, or step 3 is our last step, rather. Okay. Let me see if I can find our graph here. So this is tiny DG. Okay, so this is kind of famous, this little graph here. It's sufficiently complicated that if you look at it, it's not immediately obvious, what the strongly connected components are. But if we traced it through, we should get the answer that we saw on the previous page. And here's how that looks. So essentially 1 is by itself. These are all in one group. These are in another, right? And if we talked about this in terms of its topological ordering, we have kind of 0, 1, 2, 3, 4 as the strongly connected components. Okay. So we can barely do this with our fingers, right, on something small. Right, the algorithm could do it on something the scale of the, fruit fly brain, right? If we really had the data for that, which was my goal for today, was to get you guys access to a fruit fly brain, but I didn't succeed in that just yet. So hopefully we'll find some data like that because it would be pretty cool to kind of analyze that stuff. Okay. So high level, there are a couple different algorithms for calculating these strongly connected components. So this is just one of them. This is the one that's based on the reverse graph and topological sorting. And it kind of is an interesting approach because it just shows us that the basic building blocks that we kind of see, topological ordering, depth first search, become part of larger and larger algorithm solutions. So one of the reasons that people are so adamant that we understand the performance of the foundational algorithms is because they imply the expense of the larger algorithms that are based on them. So in this case, depth first search is an order V plus E cost, and we got to do it twice. So 2 times V plus E is still linear. It's not quadratic. And so that's why this particular algorithm is tagged as being linear, right? A 2-phase linear algorithm, okay? So, and who knows, there may be other algorithms people come up that are linearitmic, right? or maybe even, logarithmic if such a thing was possible. Okay. So that's kind of the main push. I'm just going to do a quick touch and fly over on our Euler tour thing, but let me just pause there and see if anybody has any conceptual questions on the algorithm itself. Okay. Remember the classes that we used, graph and then strongly connected component. Don't need to have the topo directed cycle in here because we have that kind of built in. Okay, so let's kind of close out by talking about the last part of homework 7. So the last part is to find out if there's an Eulerian cycle, basically. So an Eulerian tour is any path that touches all of the edges. An Eulerian cycle is a path that touches all the edges and ends back at the same starting point. So the second one is what we're looking for in our homework 7, if we can find it. So here's the idea, right? So remember the Cronenberg challenge, right? So is there a cycle? So in an undirected graph where you can go either direction, the rule is pretty simple. If the out degree is even for every vertex, then there's an Eulerian cycle in that group of vertices, okay? That's for an undirected graph. For a directed graph, it's a little more complicated, but let's just review the undirected graph. So if we count the degree of this vertex, 2, 2, 4, wait, 1, 2, 3, 4, 5, 6, 2. So if all of these are even and it's an undirected graph, then we can say, yeah, for sure, we can find an Eulerian cycle in there, okay? And there's one of them, okay? But the yes or no question can be answered trivially if we just go around and check the length of the adjacency list for every vertex, right? So in an undirected graph, if those are all even in length, that linked list, then we know we have an Eulerian cycle in there somewhere, okay? So sorry, these are the other edges. I left them out, okay? And it's kind of fun. You can trace these through with your finger too. So you'll have some quiz questions just to make sure you kind of remember what an Eulerian cycle is. But for the bridges of Königsberg, there isn't one, right? Because we don't have an even number degree at all the vertices. So it's pretty quick, to answer that question when it's an undirected graph. If it's a directed graph, it's a little different. So the directed graph, the rule is the in degree equal to the out degree at every vertex, okay? So let's take a look at 0. The in degree is 1 and the out degree is 1, right? 5 in and out is 1. In here, out is 2 and in is 1, so no. So this particular graph would not have an Eulerian cycle, right? We would have a violation there, okay? So that's the rule. So how do we apply this to homework 7? Okay, this is the part that not everybody will get. So if these are our strongly connected components, so imagine in our taxi scenario, this is the safe neighborhood, okay? So we do not care about this edge right here, and we don't care about this edge. We just want to know if it's possible to hit every edge without repeating an edge and get back home again. Okay, so we can't do it there, right? We can do it here, right? So that's a good one, right? And we can't get back home again here. So that's not really one there. Okay. So we don't care about the edges between the islands. We just want to check for an Eulerian cycle inside of the islands. Okay. So it's definitely a little tricky to do that last part. Okay. But in this graph, tiny dg, and you could test your code on this in homework 7, you should only get one Eulerian cycle, right? Which is going to be this one over here, right? That one, okay? So we have to make sure we ignore the things that are not inside of each strongly connected component. And we got to make sure that we can get back home again after visiting all the edges, okay? So traveling around and not getting back home doesn't count, okay? So think of yourself as a street cleaner or a street painter. You want to get back home again at the end of the day, okay? So that's the last part of the challenge on homework 7, okay? So not an Eulerian cycle. Okay? So just reviewing, put you in a good place. We're going to need our strongly connected component class. We're going to need the updated graph class. Sorry, don't use this. This is a little out of date. Use Canvas. Print the counts. So identify and ignore one person strongly connected components. So that's just printing out the component list, right? So what are the strongly connected components and who's in them? How many are there in total where the population is greater than 1? Okay. Print the members of each one and then determine which ones have an Eulerian cycle, if any. And you can identify them by their component IDs, right? And then print out how many you find. So as long as your output is clear and understandable, then that's great. If you just print out the adjacency list and say QED, I'm going to be like, yeah, no, not really. So I just need a little help, so I'm not digging through your code. So if you cleanly answer these questions in your output, that's all we really need there, okay? So you're going to pull in the code, do the analysis on the data, find the strong connected components, and then begin your kind of digging a little bit deeper, okay? So if you have any questions, just let me know. Again, I just need it to be intelligible. I gave a lot of details in Canvas on how the format should be, but I'll be flexible as long as I can kind of understand them. So here's your components, and those will all be in Canvas, and directed graph SCC for your cycle is going to be crucial, okay? So you're going to need to think about that. And you're going to discard contributing adjacencies that lie outside of the current SCC. Okay. Save this one for last, of course. Okay. And if any SCC vertex does not have a degree that has the in and out, then it cannot be an Euler tour. Okay. That means you're going to need to use your reverse graph, right? Because your reverse graph will have the out in degree, and the regular graph will have the reverse graph will have the in degree, and the regular graph will have the out degree. So you're going to need both graphs to do this work. Okay. And use TinyDG, and then test your ginormous graph. Okay. And I believe this is in the comments to your starter code, so you don't have to go digging for it. Okay. And I think that's that. Next time, we'll move on over to weighted graphs and talk about spanning trees. What is a spanning tree, and how do we find spanning trees? Okay. So, and what is a minimum spanning tree? Okay, which is an important graph feature that we want to be able to determine. Okay. So that is that. I think we have a lab. Don't we have a lab? Sorry, let me check. I thought we said we did. Sorry that I don't have that in our slides. Hold on. Lab 26, find strongly connected components of size 1. Yeah, so this is a small starter problem. We're just asking you to apply that and then identify which components have only one member in them. So it's not a lot of work to do, but it's going to get you familiar with this idea, similar to what you did in homework 6. But here's your data. You'll just need to build up your graph, call the strongly connected component class, print out the component IDs using the class methods, and do a quick analysis. So shouldn't be more than 20, 30 minutes of work for you. Okay. So I leave you that. Thank you for your attention, and I will see you guys on Tuesday of next week. Okay. Stop.